So let's begin. We're going to talk about geometric unity. And let's be very clear from the outset, this is not just another theory of everything. You should think of it instead as a foundational critique of the geometric language physics has been using. The proposal is audacious, really, that the universe can be derived from almost nothing, provided we're willing to question our most basic, most deeply held assumptions.
And that brings us to this question from Einstein. It's really the philosophical bedrock of this entire program. Is our universe arbitrary? Just one random ticket drawn from a vast landscape of possibilities? Or is it, in some profound sense, mathematically inevitable? The core ambition of geometric unity is to drag this question out of the realm of philosophy and put it squarely into the domain of testable science.
Now, this whole attempt is born from a frustration, a sense of a 50-year stagnation. Think about it. The critical questions Murray Gell-Mann was asking back in 1983 about particle families, about why there are generations, why this specific gauge group for the standard model, those questions are still on the table. They're largely unanswered. Instead, the field seems to have fixated on what proponents of this idea would call a red herring, the quantization of gravity, all while ignoring a much deeper geometric schism right at the heart of physics. And that brings us right to the central technical claim. See, geometric unity recasts the primary conflict in physics. It's not quantum versus classical. It's a schism, a deep divide in the very geometric language we use to describe reality. Here's the core issue. It's a tale of two geometries. You have general relativity, which is built on the intrinsic, metric-dependent world of Riemannian geometry, and then you have the standard model, which relies on these auxiliary, metric-independent structures called Eresmann-Canyon fiber bundles. And the problem is, these two frameworks are just, well, they're fundamentally incompatible. This table really lays out the fundamental bargain that was struck. On one hand, Riemannian geometry. It gives us this beautiful thing, the Levi-Cedeva connection, a unique, distinguished structure that's completely determined by the metric. It also gives us powerful projection operators. But its curse is its rigidity. On the other hand, you have Eresmannian geometry. It offers you total freedom. You can postulate any gauge group you want, but the price you pay is that it's purely auxiliary. It's disconnected from the underlying geometry of space-time itself. So, the central challenge, the real problem, isn't quantizing gravity. It's resolving this twin origins problem. The goal has to be to find a single geometric framework, one that naturally gives you both the rigidity you need for GR and the gauge freedom you need for the standard model, instead of just starting with two completely disconnected axiomatic systems.
Okay, Section 2, the observerse, a new arena. The proposed solution here, it begins by doing something pretty radical. It essentially destroys the stage upon which all of 20th century physics was performed.
Now, the idea that space-time isn't fundamental is, well, it's almost a familiar talking point by now. But the key difference here is the motivation. In this picture, space-time is demoted not for the usual quantum gravity reasons, but so it can serve as an observational slice of a much larger, grander structure, a structure from which both gravity and gauge theory can emerge together. The proposed arena is called the observerse. It's a 14-dimensional space of metrics, which we're calling Y. Our familiar 4-dimensional space-time X is nothing more than the image of an observational map, ITA, into this bigger space. So in this framework, you see, gravity isn't a force to be quantized. Gravity is the engine of observation itself. This structure also solves a very deep paradox that plagues quantum gravity. If the metric is fluctuating wildly, where do the metric-dependent spinors even live? The proposed answer is they don't live on space-time at all. They exist as these chimeric spinors on the 14D observers, premetrically. They exist independent of any single space-time observation. All right, Section 3, a unified geometric engine. If you have a new arena, you're going to need new mathematical tools. The dynamics are no longer on space-time. They're shifted to a new, much more abstract space.
So the dynamics get recast onto this affine space of connections, and they're governed by a new kind of symmetry, the inhomogeneous gauge group. The key innovation, though, is this object called the Cheab operator. What it does is it functions like a gauge-invariant analog of the metric tensor, which lets you perform contractions and build a Lagrangian.
something that was previously thought to be impossible inside a pure gauge theoretic framework.
And this leads us to the second major thesis, that physics has been trying to unify the wrong equations. The proposal is that the first-order equations, Einstein and Dirac, are the fundamental ones. The second-order equations, like Yang-Mills and Klein-Gordon, are posited to be just consequences. If you square the first-order theory, you automatically get the second-order ones. It's a kind of Dirac pair unification.
So, Section 4, answering Rabi's question. The payoff for all of this intense geometric abstraction has to be a concrete explanation for the seemingly arbitrary particle content of the standard model.
You've heard Rabi's famous question about the muon. Who ordered that? Well, you can generalize that question to the entire standard model. Why this particular particle zoo? Why these specific quantum numbers and these exact symmetries? Was it all just some contingent cosmic accident? Or does it follow from some deeper, hidden principle?
Geometric unity asserts that there is a reason, and it begins with a number, 16, the precise number of fermionic states in a single generation of the standard model. The claim is that this number is not an input you have to assume. It's a result you can derive.
Look at how this central derivation is supposed to work. The observation of the 14D observers by our 4D spacetime, it induces the splitting. You're left with a 10-dimensional normal bundle. Now, a Weil spinner on a 10-dimensional space has exactly 2 to the power of 4, 16 components. And here's the bombshell implication. The so-called internal quantum numbers of the standard model, they aren't internal at all. They are the spinorial quantum numbers associated with these extra unobserved dimensions.
And what about the family replication problem? Well, it's addressed with this provocative 2+1 model. The idea is, there are not 3 identical generations, no. Instead, 2 of them arise from standard spinners. But the third is an imposter. It's a fundamentally different mathematical object, a Rarita-Schwinger field, whose projection onto our observed spacetime just so happens to mimic a third spin 1/2 family.
So that brings us to Section 5, the provocation. This is a final summary of the program's most audacious claims, and it's a direct challenge to the very foundations of 20th century physics.
I mean, just look at this list. These are not minor adjustments. Each one of these claims represents a potential paradigm shift. The fundamentality of space-time itself, the nature of dark energy, the existence of 3 identical generations, the origin of chirality, all of them are reframed. They're either emergent, or they're illusory, or they're the result of a profound geometric misinterpretation.
And so we return to where we started, with Einstein's question. If the contents of our universe, the particles, the forces, the generations, are not arbitrary inputs, but are the inevitable mathematical consequence of a single, self-consistent geometric structure, then the answer to his question would be that there was no choice at all. And that is the ultimate provocation of geometric unity.